All right, now that we know what these maxima and minima or extrema values are in section 12.2, we're going to do applications. Yes, word problems. Yay! I'm probably going to break this video up into two parts. I'm going to have the basic lecture with a couple of examples, and then the second video will be more examples. That way, nobody has time for a 30-minute video. I've been talking too much. We got to break these up. Okay. So when dealing with costs, we would like to know a minimum, right? We want to pay as little as possible. Whereas with profit, we kind of want to maximize that. We want to make some money. These are called optimal values because they are the best possible case for the problem at hand, right? So optimization. In all applications, the first step and the hardest is translate a written description into a mathematical problem. I know you guys can solve mathematical problems. I know that many of you, or some of you, struggle taking the words and figuring out what math you need to do. So that's what we're going to work on in this one. So in the problems we look at in this section, there are unknowns that we're asked to find. There's an expression involving those unknowns that must be made as large or as small as possible. Our objective, our optimization problem. This will be our objective function, and there may be constraints or equations or inequalities that relate the variables. Like we have to have a positive side length of a measurement of a square, right? So a math problem might give you a negative answer, but the reality of the actual application means we can't have a negative. So we look at things like that. In order to solve application problems, or optimization problems, we're going to follow these steps. We're going to identify the unknowns, possibly with the aid of a diagram. A diagram is not always necessary. Identify the objective function. This is the one that will say things like maximum, least, most, minimum, those types of identifiers. Identify the constraint equations. These are equations that relate your variables or known equations, like for volume of a cube or something, that'll help us out. We got to state the optimization problem, reduce it down to just basics, eliminate any extra variables if we have them, and then we can use the derivative to find the absolute min or maximum of the specific objective function. So let's start with no words. Here's a problem. How do we solve it? So we're going to maximize p equals xy. P is just the function product, the product of two numbers So I want the maximum product of two numbers where those two numbers had to be 10. Okay, our objective function, wow, I still can't talk today. Our objective function is the p equals xy, and it has two variables. Yes, it's p, right? But the variables are over here. This is the name of the function, p product. These are our variables xy. Well, we need to try to substitute for one of them. What can we use? Here's our constraint equation. Our constraint says x plus y equals 10, or if we wanted to, we could solve for one of the variables. I chose to solve for y. Y equals 10 minus x. I can substitute this into our objective function, right? P equals xy. P equals x times y. Oh, y is 10 minus x. Distribute, x times 10 is 10x. X times a minus x is a minus x squared. And we know that to maximize this function, it's a parabola opening downward, it will occur at a critical point. So we're going to find the derivative. The derivative of 10x minus x squared is 10 minus 2x. That's driving me nuts. I'm going to have to stop pointing with that. 10 minus 2x. To find stationary points, I set the derivative equal to 0. Add 2x to both sides. Divide by 2, and I'll find x equals 5. The derivative is a polynomial, so there are no singular points. Reasonable endpoints. If I have two numbers that I'm multiplying and they add to be 10, maybe 0 through 10 would be good solutions, right? If x is 10, y is 0. If x is 0, y is 10. So they seem to both range through 0 to 10. Reasonable based on the problem. So I set up my number line so I could do test intervals. From 0 to 10 is my reasonable endpoints, are my reasonable endpoints. X equals 5 is a stationary point. I'm going to choose any value between 0 and 5, and I choose 1 because 1 is one of the easiest values I could do arithmetic with, or algebra in this case. Evaluate the derivative when x is 1. I'll have 10 minus 2, which is 8, which is positive. That's all we care about. The function is increasing. Choose any number between 5 and 10. I chose 7. Maybe you're one of those people that want to choose like 8.3. Go ahead. Evaluate 8.3 in the derivative. It's no big deal. You can still do it. I chose 7, so 10 minus 2 times 7, that's 10 minus 14, that's negative. So my graph is decreasing there. Negative slopes, decreasing graph. So from the first derivative test, I see that I have a maximum. All right, so my maximum occurs at 5. I set my derivative equal to 0. I know this is an extrema. I had to test to make sure it was the maximum that I wanted to. So 5 times 5 is the largest product we could have, where the two numbers 5 and 5 add to be 10. So a maximum value of p when x equals 5, and our y value is also equal to 5. And we should say maximum value of p equals 25 when I have my x and my y values. All right. Let's do another one. The application word was on there. That's right. Don't look at that yet. Let's minimize the function f. This is actually based on a famous sequence, I believe. F equals x squared plus y squared with the constraint that x plus 2y equals 10. All right, so what we want to minimize has two variables. Let's get rid of one of them. The way we get rid of one of them, or substitute or eliminate, or better words, I'm going to solve x plus 2y equals 10 for one of the values, one of the variables. X is the easiest to isolate because I'm just going to subtract 2y from both sides. So now my f equation, f equals x squared. Instead of x, we're going to call it 10 minus 2y all squared plus y squared, finishing the function. Here's my function. I can multiply this out, combine like terms, get it into a nice polynomial, and you are welcome to do that if that's your style. But I also know the chain rule. So if I have my function in a single variable, I could just take the derivative and then simplify it. Instead of simplifying then take the derivative, that looks hard. I'm going to take the derivative then simplify. So chain rule says bring the 2 down in front. Leave the 10 minus 2y alone. Derivative of the inside. I did bring 1 down here, right? 2 minus 1. Derivative of the inside plus derivative of y squared is 2y. The negative 2 times 2 is a negative 4. I still have my 10 minus 2y and my plus 2y. When I distribute, I'll have negative 40 plus 8y plus 2y, and that gives us a total of 10y minus 40 for my derivative. Sometimes calculus then algebra easier than algebra then calculus. So when is my derivative equal to 0, right? My relative extrema are always going to take place at critical numbers. Critical number, the first one we look at, when is the derivative 0? It's polynomial, it's never singular. It's 0 when 40 equals 10y or y equals 4. I didn't even put a reasonable restriction on my values. I'd say x goes from 0 to 10. Y is probably going to go from 0 to 5. I don't know. But let's check out, what if it was just anything, right? Any number line. Well, here's my critical value of 4. Let's choose a value to the left of that, 3, and a value to the right of that, 5. I could have chosen 0. I could have chosen 793 if I wanted to. But why? 3 and 5, they're close to 4. They're easy values to use. Those are the values that I chose to use. All right? I chose, which means you don't have to use those same numbers. You could choose harder numbers if you want to, but I generally try to choose the easiest when I get to choose. If I evaluate my derivative when y equals 3, I'll get a 30 minus 40, which is negative. If I evaluate my derivative when y equals 5, that's 10 times 5 minus 40, or 50 minus 40, which is positive. Do not care that the answers are 10s. I only care about the negative or the positive, because a negative tells me I have a negative slope. A positive tells me I have a positive slope, so I am decreasing and then increasing. My derivative changes sign when y equals 4. This indicates that y equals 4 is a minimum, and a minimum is exactly what I was looking for. F has a minimum at y equals 4, and what's my x value? X is 10 minus 2 times 4, or an x value of 2. Excuse me. Asthma in the fall. Also, we might say that f is equal to 2 squared plus 4 squared. That's 4 and 16. 20. 20 is the minimum value. It happens at x and y. Is the minimum value, that's always the output. Where it happens, the at, that's always the input, the variables, the independent variables of the function. All right, let's do one application problem, and then I'm going to send this into to YouTube for YouTubing, and then I'll do a second video of more applications like this. All right, so assume that no accounting for grammar, assume that it costs Microsoft approximately C of x equals 14,400 plus 550x plus 0.01 x squared dollars to manufacture Xbox 360s in a day. Why are they still manufacturing Xbox 360s? Some of us just can't let go. How many Xboxes should be manufactured in order to minimize average cost? Average cost. Don't forget, average cost is the total cost function over x. And if I want to minimize average cost, this will be my objective function. I also want to know what is the resulting average cost of an Xbox. Give your answer to the nearest dollar. So this tells us how to answer. So it turns out that the C of x is a constraint. It's an equation that's going to help us with our objective function. The average cost function is total cost divided by x. So I will divide 14,400 by x, 550x by x, and 0.01 x squared by x, and simplifying into a form that I can use for a derivative, because I know that my extrema, my maximums and my minimums, will always occur at a derivative. So I'm looking for or the derivative is 0, stationary points, or where the derivative is undefined, but the original function exists, which are singular points. Take the derivative. C bar prime of x is a negative 14,400 x to the negative 2 plus 0 plus 0.01. I can rewrite that as negative 14,400 over x squared plus 0.01. The only singularity of our original function, the only time this derivative doesn't exist is when x equals 0. It's not actually a singular point because it's not in the domain either. It's not actually a singular point, but when you haven't made any product, there's no average cost either. It's one of those weird situations. I know that C bar of x equals 0 when negative 14,400 over x squared plus 0.01 equals 0. So the first thing I did is I subtracted 0.01 to both sides here in gray. And then to get rid of the x squared, I multiplied both sides by x squared. So really what I'm doing is I should have added this to both sides. It would have been so much easier. I'm trying to get the x by itself, right? I subtract the 0.01 from both sides, multiply both sides by the common denominator of x squared, and then divide by the negative 0.01 to get x squared equals, there we go, 1,440,000. If I take the square root, that one's really nice. X equals plus or minus 1,200. Now, do you think maybe Microsoft should manufacture negative 1,200 Xbox 360s? I don't even know how that's possible. So it's unreasonable in this situation. We don't even consider it. But the math says that happens, even if the application itself doesn't say that happens. So our minimum average cost is when x equals 1,200 Xboxes are manufactured. The resulting average cost per Xbox is C bar at 1,200. So C bar at 1,200, I evaluate it here, and it's $574 per Xbox 360. This is exactly why the prices are so high for the initial release of a product, right? In order for them to keep their costs as low as possible, they have to increase the price, right? It's just the way it goes. They have to cover their costs early on. All right, that's about 15 minutes. That's about all I would really like to do for any of your videos. So I'm going to wrap this one up and send you some more examples in the next video. Same section, more